Okay. Hello, everyone. I'm FX from the German hacker group Finolid, and I'm here to give you an overview on bug hunting techniques, or more professionally phrased, vulnerability hunting techniques. We all know that the common goal is often just to have O-Day. Now, you can be socially, you can try to approach this socially by talking to people who have O-Day. What's this? So why do you just... Okay, we just found the bug in PowerPoint. I award a beer for whoever can exploit that. Fuck! So, do you stay here? Has anyone seen this before? You have. Do you have a countermeasure? I hate it. Okay, let's do it this way. That works. Okay. Damn technology. So, back to the topic at hand. Having O-Day either requires you to spend a lot of time on IRC, or reading bug track and hoping that people do not patch their systems, or you're a bit smarter and write your own. Which is the fun part, of course, but also requires you to have vulnerabilities in the first place that you can exploit. So what we are looking for is something that handles network side input anyway. Could be user input coming in on a console, but that's kind of boring, so we're looking for network side input. We're looking for something that runs on a remote system, because as we just saw, exploiting yourself is kind of silly. And we look for something that's complex enough to potentially contain vulnerabilities in the first place. Well, with the exception of some small UDP services on Cisco iOS, it usually doesn't make sense to have to try to find a vulnerability in a UDP echo service. So you should actually look for something a bit more complex than that. So what environment are we talking about? For the purpose of this talk, I'm concentrating on Windows NT, 2K, or 2003 server. Mostly those are closed source binaries, often in the form of NT services that are fairly large, and sometimes do forking. This is quoted here because, well, in Microsoft there is the concept of spawning a child, but it's not called a fork. It's called a create process A or create process as user A, but that doesn't work as a verb, so I call it forking. We also look at application frameworks like the famous ISAPI plugins that usually are highly secure code and never exploited. Or other large-scale frameworks where people actually reinvent the wheel and implement all the basic functionality that's usually coming out of libraries themselves for portability reasons. As an example, SAP is such a beast. Or, on the other hand, it could be a widely used client. So what obstacles are we facing? The Windows 32 API is extremely large. If you ever installed MSDN somewhere, you know that you need a certain amount of hard disk space. We have fairly large binaries. Compared to Unix systems, the binaries on Windows tend to be really big. So even if you throw them in IDA, it takes a lot of time. We have compiler specifics. So the same binary might be different depending on which compiler you're using, which settings you're using, which compiler version. We have sometimes the situation that a vulnerability is exploitable if it's compiled with one compiler and not if it's compiled with the other, stuff like that. We have the use of library functions in code. What I mean by that is you actually have in shared libraries exported functions like sprintf or whatever, but often those functions are, for performance reasons, from the compiler compiled into the main binary instead of being called out of the DLL. In the same line, we have function inlining, where you don't even have the function anymore. We have vendor-specific libraries, as I just said, like SAP does for portability reasons. Oracle, I think, does the same. And we have unknown protocols that we might want to exploit that might include encryption and stuff that's really not documented, or any other vendor-specific obscurities. I'm sure you all have seen very obscure things done by software vendors. So what testing methods do we have? We have manual testing, pure old style, get your hands dirty. We have fuzzing, static analysis, diffing of binaries, and runtime analysis as the general topics. So let's start with manual testing. The idea here is to use a standard client or whatever counterpart. So if we're attacking a client, it's kind of pointless to use a client to attack it. So in this case, we use the standard server to access the target service, whatever we're trying to attack. And then we look for behavior. For example, we look for valid input behavior and invalid input behavior. This is really important, especially the first part is often overlooked. You should actually know what it does when you put valid input in there. We look for timing. How does it react on different timings? Network communication. Obviously, if you have a client-server system and you want to manually test it, you should actually turn on a sniffer. It doesn't really make sense to just use the client and click around and see what happens. You should actually turn on the sniffer and see what goes over the network. What we are most interested in is communication that happens before authentication. Why? Because otherwise we need a username and a valid password to trigger the bug in the first place. So what we're interested in is stuff that's handshaked or whatever before a username and a password is validated. We look at common configuration tasks and failures. This is very important, and this is one point that makes manual testing very effective. If you're manually testing this, you're often required to first set it up. By setting it up, you actually find out how the configuration works and what shortcuts exist that people might take. Example here, if you were to get yourself into security and you look at Apache and you look at CGIs and you have a CGI and it doesn't work, many people first go to the CGI directory and say change mod 777, which of course makes it work, but of course is only recommended by people who don't like you. So actually there are even manuals for large-scale software that recommend doing this as a first step if it doesn't work. So you get familiar with the configuration and you get familiar with the tasks that you need for administration. So what you try to find out. First of all, you try to find out states in the target. That's your general goal. You first want to see reactions to valid input. What happens if I do what I'm supposed to do? And then reactions to invalid input. You look what happens when you change the timing. And especially in all three of those, in what context this is with data transmitted over the network. So you enter something, you look what goes over the network and when. You see the runtime requirements of the target. Of course, if you set it up, you figure out what you also need. So you might be required to install something that you could use as an attack vector. Let's say you need to install a SQL database for the target to work in the first place. Default configuration and misconfiguration issues, I just mentioned those. And you're interested in the logging capabilities. You're really interested in the logging capabilities for two reasons. First, logging code is prone for errors. Not only format strings, but also buffer overflows. Lots of buffer overflows actually happen when the target application tries to write a log. Also, you're interested in how much logging can I turn on and off for two different reasons. First, what's the default logging? Because if you got the O-Day, you don't want that the log contains all the information how your O-Day works. So you actually want to know how much the other side knows when you're finally done. The second part is, if you can turn the logging to full debug mode, you might not need to reverse engineer anything, because often it will tell you, this is tcp-com.c line 400, I just received a packet. This is tcp-com.c line 4000, I just successfully parsed the packet. Yeah, you don't need to reverse engineer the packet parser if it tells you what it is. Things to look for. Input validation on the client side. Very common thing. You see that by input in the client rejected without having any network communication taking place, or you have input that's in the client and is modified before sent over. Typical example is web applications where the client is the browser. If you get a JavaScript pop-up saying you're not supposed to enter 500 A's here, this is client-side security. This is interesting because the target might actually expect that the client handles all the input processing and input validation. So you want to know if the client does this or not. The same with the modified data. Here, for example, if you would enter a space character in your browser's URI field, your browser would actually transform that to a plus or %20 and before transmitting it to the server. Now, you might actually want to try what happens if you directly send a space character to the server. Pre-authentication client data that could be sent, typical stuff to look for is host names, of course usernames, certificate content, which is really becoming more and more important because people are putting crypto on their protocols and doing client-side certificates or server-side certificates and make it really, really secure. And then you have the certificate that contains strings, such as distinguished names and stuff. And you have a longer distinguished name, put it in the certificate, send it to the server. The server takes the certificate, parses it, takes the string, copies it into a fixed buffer, and crashes. Datetime strings, also fairly interesting because they're often transferred as text, and you have various interesting results when your date is not limited to 24 hours. So if your day actually happens to have 4 billion hours, some servers react fairly interesting. Version information, it's the same deal. Often the version of the client is transmitted so the server can actually find out if this client is an older version, and it gets really interesting if this version is supported by the server. Typical case here in SAP, they transmit version information from the client to the server, and you can basically, in a communication back and forth, decide for any given packet what version it is, which of course produces fairly interesting and not planned for data flow scenarios in the server, which of course are in this case readily exploitable. More things to look for. Network protocol structure. While I did really look at the protocol, you first try to find out if field sizes, protocol field sizes, are dynamic or static. If they're static, then it's a less interesting target, but can still have problems, because if it's really static, then the programmer might actually have allocated just enough to have this static field covered in the software. And as soon as he receives more data, he might actually copy it somewhere, the typical thing. Or field size determination. Here we have an example. Over here, let me just walk down here. If you see something like this, you have 4 characters, 3 of them 0, and then the 4th having a number, in this case 8, and then you have 8 characters following it. This is obviously a length field. So this is interesting because there's also a 0 following here. Now we have 2 different points of information for the same information itself. It's 0 terminated and it got a length field. This is fairly common. Don't underestimate that. This is very common in half binary protocols, because you have then pieces of software that look at this field and take this field as the information how long the string is, and you have other pieces in the software that actually use standard C library string operations and rely on the 0 character being there. So, of course, the idea here would be to replace the 0 character with something else, or put a different length in. We have information grouping, which is a bit hard to explain, but for those of you who know ISA KNP, this is a classic example. You have lots of different information which can again contain information, which can again contain information, which creates a very complicated parsing scenario. And this is usually very bug prone, as easily seen if you look at any given ISA KNP implementation. And of course, numeric 32-bit fields become interesting as soon as you set the most significant bit, and well, it might become negative in the code. Timing, for example, concurrent connections. Of course, if you have many concurrent connections, they might trigger behavior that's not planned for. If they, for example, keep a table on the clients they are serving and this table doesn't scale right, you might actually find something. Or fast sequential connections. So what are the advantages? You don't need any additional tools. You don't have to code anything. You don't even have to really know what you're doing. You can just take the client and the server, click around in it, and see what it does, and actually might find vulnerabilities. You become familiar with the target. This is very important. The more you have to work with the target, the more you understand the concepts behind it. And this is the reason why all the kiddies do HTTP service and FTP service, because they're able to read. They can download the RFC, and they know how HTTP works because that's how they got the RFC in the first place. This is the reason why so less people write exploits for Cisco, because even the people who work with Cisco on a daily basis don't know why it boots all the time. So it is really important to become familiar with the target. It is unintrusive. If you want to play with something and the server is not actually located in, let's call it, your administrative domain, it is better to use the given client because, yeah, it's more IDS friendly. It uncovers client-side security really quick. It's easy to correlate your action with stuff that goes over the network. It takes the configuration into account, what no other bug hunting method does. And of course, it gives you a high abstract understanding of the principles behind this piece of software. Well, it's slow. It takes a while. And you potentially have a high learning curve. For example, I guess that David Litchfield knows a whole bunch more about Oracle configuration than most DBAs do, because he needs to configure all types of Oracle servers all the time. But you have to learn that in the first place. It's fairly incomplete, of course, because you only touch code that you clicked on. And if this button is not existing in the client you're using, you can't trigger the functionality behind it. And it often just provides clues. as seen on the protocol example, we have now some clues where we could look for vulnerabilities, but we still can't trigger a vulnerability or prove its existence. And therefore, it has a fairly high dependence on the person actually doing it, which translates to, sorry, brain required. You have to understand what's going on behind the scenes, and you have to be able to judge from a client-side output what's going on the server. So you usually find what? Cross-site scripting easily, code and SQL injections, same thing. Protocol-based overflows and integer issues as seen. Application logic failures. This is interesting because no other technique allows you to find application logic failures. Why? Because no other technique requires you to understand the application logic. But application logic failures are really becoming more and more interesting, especially in things like Java web applications that are usually not exploited using buffer overflows or, well, sometimes integer, but not too often, but often just have pure, simple, stupid logic flaws that you can exploit and still order your favorite item for $0 and free shipping. So it's best suited definitely for web applications, proprietary clients where you don't want to sit down and write the whole protocol again, and as seen on Bugtrack for Internet Explorer. Fuzzing, different concept. The idea here is basically to create a rough client that really exceeds the boundaries of the existing client, and in the best case actually automates the process. It is an attempt to find vulnerabilities by really trying everything possible, every sick idea that you might have concerning the protocol. Again, observing the behavior, but not so closely. Often you just look for timing and you just look for things that crash. I split fuzzing in semi-manual and automated fuzzing. Semi-manual means actually writing a script, for example, that talks HTTP using ELSA or Perl or whatever you like, and then manually changing single items in the data you send and look for the results. Automated fuzzing, of course, different concept. You write a single program or script that does an iteration through all different types of SIG input that you can send over, and you dream it up before, and then you have it run and wait what happens. What you try to find out for semi-manual fuzzing, you're first looking at unexpected responses. If you request the file not here.txt from a web server and it says 404, cool. If you request the file not here.txt and it says you got blue hair, this is unexpected. And you need to find out why it is complaining about the color of your hair instead of the file not found. You look for modified data in the response. Again, example web server, if you request a file and put a special character in there, and it says file not found, and represents the special character by using %XY notation, so HTTP encoding. This is interesting. This is something you really want to investigate further, because you send 1 byte, and it needed 3 bytes for the answer. So it might actually miscalculate the amount of data that it needed, the amount of space that it needed to represent the data differently. So you want to really look for modifications in the response. Change timing behavior. If you send 10 A's and it takes 1 second, and you send 100 A's and it takes 10 seconds, this is interesting. You might actually not be able to use that directly to exploit something, but you might be able to use that later on to make it busy in the first place and then do something different with a different thread. Memory leaking comes to mind. And of course, in both scenarios, you look for target crashes. Yeah, shut up. Procedure here for CMI manual. Get your script to work normally. Seriously, that's the most important point. I've seen so many people trying to find a vulnerability with a script that didn't actually trigger the normal functionality in the first place, which of course wastes a lot of time and doesn't get you anywhere. What you want to do is make sure the script actually works. When it works, then you can start fucking around with it. Change the fields one at a time. Don't go ahead and change like 500 fields at the same time, because then you have to backtrack why it crashed. Then basically send it over, generate the output, create the file, send the data, whatever. Inspect the results, change the fields again, and do it according to the results. If your first result is this is a Java application, stop trying to find buffer overflows. And then repeat the steps, which we do sometimes. So here's an example. This little bug creeped out of under a DLL that is part of Symantec PC Anywhere. So by lifting the DLL, you find this little bug running over your table. It is a timing issue. And it is a interesting timing issue because it's not concurrent connections, but fast sequential connections that trigger a interesting behavior, because PC Anywhere needs to inform the user of what it does. This is done by changing this little icon in the tray bar to something different. And PC Anywhere needs to load the DLLs and unload the DLLs. And you know what? You do that 10 times and it fails to correlate those two actions correctly, and then basically tries to call empty space, which of course causes the user to be informed about something different, a application crash. Automated fuzzing procedure. Define what vulnerabilities you want to look for, because you have to create a script that will iterate through all your SIG ideas. But make sure that you understand your SIG ideas in the first place, because otherwise you don't want to try to fix a fuzzing script afterwards. Then you have to create the iterator script program, mostly using a fuzzer framework, which basically takes all your ideas and tries them either sequentially or in combination. You should actually try to implement it in a way that it first tries your ideas sequentially and then combine them in deeply iterated loops, because otherwise you again have the problem of later finding out what went wrong. Wait until the target crashes. Unfortunately on Windows, this needs a debugger, usually, because we have this magic called structured exception handling. So many applications just try to handle their mistakes themselves and do as if nothing happened. No, I didn't overflow buffer. So for this to catch, you need a debugger attached. And you have, therefore, issues with processes forking on Windows, because most Windows debuggers do not support following the fork process. Sometimes you don't even know if the crash happens in the parent or the child process. So what you actually need is a debugger who can dynamically do that, or you have to be really, really fast. Fuzzing frameworks. Now we get problems. Shall I try this again? No, I shouldn't. Okay. Now, the first and most well-known fuzzing framework is Spike. Written by Dave Vitale. It is, as far as I know, currently in 2.9, unless he released the 3.0. It's a block-based fuzzer written in C. Unfortunately, the programs, the fuzzing programs that you write have to be in C as well. So it provides rudimentary functions for sending data, for iterating through strings, making big strings, and that's pretty much it. Unfortunately, there is almost no documentation on it. Fortunately, it is widely used, so you can find a lot of programs that other people wrote, and you're unfortunately required to read them all to understand how Spike works. But it comes with a number of demo fuzzing programs for different protocols. So if you're new to this concept, Spike is a good starting point because you can actually see what type of data is generated and what form is usually used for fuzzing. This is another fuzzing framework written by Michael Eddington from IOActive. It's called Peach. It's currently, unfortunately, still pre-release state, but it looks really, really good, so I assume it's released very soon. It's written in Python, and it is completely object-oriented. This is good because it consists of 6 types of objects, which are generators for generating elements, protocol messages, static stuff, transformers for all kinds of transformation, encryption, stuff like that, which is really handy because, yeah, if you try to fuzz a HTTPS only server, you don't want to re-implement SSL yourself. It has protocol objects for maintaining state over time, publishers for sending this stuff or writing it to files, and groups and scripts for even more abstraction. And luckily, this is documented. So as soon as it is released, get your fingers on it. What's good about fuzzing? CMA manual fuzzing has a very good result due to the try and inspect procedure that you're doing. Especially if you're dealing with web applications, this is a very good procedure. Why? Because you send something there, you see what happens to the data, you get an idea of what type of code you're dealing with and what type of coder you're dealing with. Because basically what you try to do in bug finding is to hack the coder's mind. And if you have no direct access to the target itself, just network access, then you need to remotely read his mind. And this is where CMA manual fuzzing is very, very effective. It has, of course, the same advantages as manual testing because you keep understanding more and more about your target. It has the ability to prove the vulnerability because if you send a bunch of A's and it crashed, you slap in your shellcode and a return address and see you just promoted your fuzzing script to a ready-made exploit. Automated fuzzing. The process guarantees a certain level of coverage. This is important if you're dealing with code that you don't want to have a O-day for, but you're interested in the vulnerability because it is, for example, your own code. There, fuzzing is really good because it throws a lot of shit on your application, and at some point in time, it might crash or not. But afterwards, you can still look at the fuzzing script, and you still have all the information there, what you tried. So it is quick. It's automated. It's fast. It generates about, a few hundred SIG messages per second. And it's very effective when it comes to a high number of possible combinations. Again, HTTP as a example, you have many, many different fields in HTTP, most of them optional, and you can try all the combinations with different information and different information length. In Peach, you even have code reuse for the known protocols. So you actually implement a protocol once, and then you're done. On the other hand, understanding of the underlying protocol is unfortunately required. So you need to know how the protocol works in order to write a fuzzer in the first place. It is incomplete coverage in terms of code because you, again, only touch functionality that you trigger from the outside. You don't see anything that you didn't touch. If there is a buffer overflow in a CGI handling routine and you never asked for a CGI, you don't find this. Automated fuzzing has a few more cons especially that you need to write the test scripts, and you have to take target-specific into account. So what the problem here actually is due to the fact that you generate that much crap in the first place, you can't predict how the target reacts to it. Now, you could have the effect that, for example, generating a specific type of lots of crap will cause the target to plain simply reject what you tried. Example, again, if you try to attack a web server, this web server might have the limitation of a maximum request size, or might have the limitation of a maximum URI length. Now, if you don't keep that in mind, your fuzzer might be totally incomplete because it tries big things, but always like 5 bytes more than the maximum request size is. You never find a buffer overflow. And of course, you need a debugger, as I said, on the target. And in automated fuzzing, you often have the problem of one bug hiding behind another. I had this problem once. You send 500 bytes somewhere, it doesn't crash. You send 5,000, it crashes. Then you investigate and find out why it crashes. And it happened to be a vulnerability that was not exploitable because I was overriding structures that were only read from later on. So it didn't get me anywhere. But later, I discovered there was another bug hiding by just sending 1,000 bytes because I didn't overwrite the structures then, and later on in the code had a buffer overflow. So you can have a bug hiding behind another, and this is easily overlooked with automated fuzzing. Usually what you find, application level overflows, format string vulnerabilities are easily found with like almost any method. Things like path traversal and other things that almost go into the area of application logic, but are still so common that you can automate them. And it's best suited for services with documented protocols because, as I said, you first have to implement the protocol. Things like HTTP, FTP, whatever, web applications, just with semi-manual fuzzing, as I said, and protocols with many combinations that you don't want to try by hand. Now, static analysis is pretty much the oldest way of finding vulnerabilities, and here at Black Hat are a number of people who can tell you a lot more about it than I can. But the basic idea is you take a disassembly of the target, basically read the code in order to find vulnerabilities. This is often done by looking for vulnerable code sequences, and here's the big difference. This first looks for code that's vulnerable in the first place and then cares about how to trigger it. In some cases, you actually have to back translate the whole thing into some higher abstraction level, either a meta CPU, as some people do, or in play C language. And it's often paired with automatic analysis later on that you look for calls to vulnerable functions, stuff like that. It's always a manual procedure with the aid of server tools. So what you need is first you need the binaries of the target. Then you need the interactive disassembler, which is a commercial tool. One could argue that you can use a different tool, but I would say this point is not open for discussion. Anything that's serious static analysis should use either. You should actually have a library reference of your target. There is no point in disassembling a binary and look at calls to vulnerable library functions if you don't know what those are and how they work. So better get the documentation on the target system you're dealing with. And, well, you should be fluent in assembly. Identification of vulnerable code. This is a very common practice. What you do is you look for references to functions that are usually used to write code that others can exploit. For example, string copy, sprintf, whatever. You check the call arguments. First, you make sure that it could potentially yield a vulnerability. So in this example here, it would be the %s. You check if this is user input or not. So if you can't influence the data, then there is no point in further investigating, because if that's a fixed string that's sitting in the binary, you could only influence that by changing the binary. If you can change the binary, you're already done. And find limiting factors. If you have a string copy into a fixed buffer on the stack, but before the string copy takes place, someone checks if it would fit into the buffer, this is a limiting factor. It limits you from getting root. So check that as well. Other uses, you often use that for reverse engineering protocol handlers. What you do here is you find a known function that retrieves data somehow from the network. You find out where the data is stored, and then you follow the program flow to eventually find the place where the data is parsed, if at all. And then, unfortunately, you have to sit down and reverse engineer the whole protocol handler to find potential parsing mistakes. You can do code flow analysis. Those things listed here on the slide are actually all done by this nice little lady up here. So this is the reason why I said get IDA. Code flow analysis follows branches and calls to actually identify calls and builds flow graphs of the function and of the whole binary. It identifies the functions and hereby identifies stack variables and stuff, so your reverse engineering becomes easier. It will also automatically identify library calls, which is really handy and needs to be done to identify the unsafe library call references. And yeah, with a little bit of scripting, you can automatically identify format string vulnerabilities, but that's really easy. The good part about static analysis is it is complete and it is a in-depth analysis. So if the product you're testing is your product, this is really good, because often things go wrong because the compiler optimized something out that you didn't want it to optimize out, or other compiler-specific things. This cannot lie to you. This is true code that's passed to the CPU in this way and no other. So if you completely reverse engineered one of your functions, you know exactly which bit is going to be where, when. You find vulnerabilities that are normally not in the code that's executed in a normal case. So if you have a piece of code that's only executed in a very, very special case, you wouldn't find that with any other method. Because with any other method, you would have to think of the case first and then send the data or trigger it somehow, which is not required for static analysis, of course. You first identify the vulnerable code and then try to find out under which circumstances this code is triggered. It finds advanced vulnerabilities that no other method finds. You see integer overflows and wraps really quick in a disassembly, which you don't even if you have the source code. Off by one errors are often found only in static analysis, and complex combined vulnerabilities. There are a number of vulnerabilities that are not straightforward copy over return address and you're done, but just happen in very complex scenarios and can only be exploited if you do exactly what's required, which again is only found by static analysis. And as I said, you have complete coverage. So if that's your code, this is good. It is extremely time consuming, more than any other method, and it requires a bit more than brain. It requires experience and skill, and those are not so easy to find. You have to do that a lot, and it really takes ages to completely reverse engineer a single protocol handler. Disassembly is never perfect. You have library calls and inline functions that are not identified. The identification fails, and you don't know that this is sprintf, which is really bad, because first of all, you start reverse engineering a function, and 2 days later you find out this is the one creating pop-up windows. Well, this is probably not the one that could be exploited. Leave alone with this laptop here, maybe it could. You have multiple levels of indirection, C++ code, Delphi code, really bad. You can almost not read the code at all. If the code flow analysis fails because there is some protection or packing or whatever other obfuscation magic employed in the binary, you're almost screwed. And structures, advanced data structures, something dynamic, is very hard to identify what it is and what it does. It is also not usable for higher level languages. So if you got a binary that's Visual Basic, you don't throw that in IDA. If you do, good luck and get some aspirin. Usual findings. Protocol level overflows. Of course, if you reverse engineer a protocol handler, you might find a vulnerability in there. As I said, complex vulnerability and integer overflows are really easier to spot in disassembly than they are in source. Best suited for protocol parsers, unknown protocols if you need to find out how it works, code using unsafe functions in unknown locations. Here's an example. Let's first look at the code here because I have to delete it afterwards. Here's someone took user input and put it into his printf with a static buffer on a stack, and we have, this is a classic case of a SIG Intel instruction. Those instructions should not exist in a sane CPU. You have the stack pointer, then you have a EBP offset, which we see later here is fairly dynamic. Fixed offset for the stack frame and a fixed variable. And now he sprintf something in this buffer, then adds to the offset the number of bytes written, and later on does the same with other user input. In this case, it was that a single user input here, the argument, could not be big enough to overflow the buffer. But of course, multiple user inputs of this type could. So what is it? It is a fairly funny web server. The reason we started to look at this is actually Bugtrack. Someone posted a message to Bugtrack complaining about a denial of service attack against this web server in the version 0.5.9, saying that if you requested a URI with lots of A's, the server would crash. The author, of course, put a note on his website that there is a new version, 0.6, which fixes the denial of service vulnerability, and all the vulnerability databases have this as a denial of service vulnerability. Fun part, of course, if you attach a debugger and send a bunch of A's to it, guess what? You find a bunch of A's in EIP. So this should teach you something about the quality of some security research. And so we started to look at it, and it contains a lot more of those little beasts on the left. So in this case, it was a buffer overflow in the combined logging. The stuff that was sprintf'd and added were actually the different fields that you have in combined logging, which is user agent and refer and stuff like that. And of course, that's a NTE authority system remote. Another method, diffing. Diffing is identification of a vulnerability after it has been fixed. So the goal here is basically to find what vulnerability was fixed. And we had a talk already on this, so I'm pretty quick on it. Reasons, of course, vendors do not notify the public, so you might want to know if they fix a buffer overflow vulnerability in their code or not. And silent vendor fixes don't actually guarantee that the fixes do work. I had this case myself in a commercial application. They had a buffer overflow. I told them about it. They fixed it silently and fixed it in the way of like keeping the code the way it was, as printfing something over the stack, and then later on checking if the return address was overwritten. If this is the case, they call it abort. Of course, such a fix is not really what you want, so this is where diffing comes in. And there are still various reasons for various people to get exploits on things that are already fixed. I guess you can imagine a few. In patches, you need to find out what file is actually modified. Of course, for a single file, that's easy. For a bigger number of files, like Microsoft Service Packs, you need to monitor that. So you could use filemon from sysinternals to see what's actually done to the files. And for other update procedures, if you're looking, let's say, for vulnerabilities in code that's in mobile phones or stuff, they often don't want you to have the code, so they delete it after the update procedure is done. So the best thing here is actually to kill the update software before it's done, or you do a static analysis of the patch. This is high-verse domain, comparing two versions of binaries by hand. Forget it. I just skipped this part. Don't do it. There's automated binary diffing, and that's the graph-based stuff that Harvard presented today, which is the recommended way of doing it. So runtime analysis is the other side of the coin. You do an inspection of a running target in its environment. And you identify vulnerable code sequences using disassembly, just like in static analysis, with the difference of observing the code running in its native environment. This has the advantage that you actually see what data it is dealing with right now. So you don't have to reverse engineer everything from the beginning on to find out how the data got there in the first place and if this is user-provided data or not. But you actually have to, you actually can see if this is data that you provided in the first place, and if not, just skip it. It is again a manual process. The requirements are even higher. You need a functional version of the target, which is sometimes difficult. You need a debugger on the same platform. You again need to be fluent in disassembly or in assembly, and again need a library reference. So for the debugger part, I thought it would make sense to come up with a debugger that people can use, because I realized there is no open source debugger for Windows. There are just debuggers with APIs, and those APIs tend to suck badly. So I wasted a bit of my time and wrote a open source Windows debugger. It's a C++ class structure, so you can easily integrate it into your code. The idea is to provide you with the boring tools already done, so you can write the non-boring tools. It supports PE parsing, disassembly, thread handling, breakpoints, and everything you expect from a debugger. And it is meant for instant debugger creation. So here we have an example. This is a full-blown Windows debugger. This is all you need to do. You basically tell your C compiler where to find the info on a debugger. You create one, you attach it somewhere, and you let it run. This doesn't do anything except for tracking exceptions and other stuff, tracking loads and unloads from DLLs and everything you expect. And now here in between, you can write your code. If you want to see what happens, let's say, with an access violation, you can either register a callback function that's called with the full information on the exception happening, or you can overload virtual functions provided by the class. So in the hope it's useful. Then for runtime analysis, we have two different ways of doing it. We have data follow procedure, which basically doesn't care about which code calls which code does which code, but cares about what happens to my data. What you do is you look at the point where the data actually came in the first place, and then try to find out what happened to the buffer by usually setting memory breakpoints at the buffer, and then have the debugger run and see when it came back and say, wait a minute, here's a piece of code that touched this data and wanted to read it. It will read the data for two reasons. Either copy it somewhere else or start parsing it. So what you do here is quickly identify the parsing function instead of, with static analysis, follow it through. And you can actually use it to craft data that could potentially trigger a vulnerability. So instead of sitting down and writing a rough client to send the data, which could take ages depending on the complexity of the protocol and other factors, you basically stop at the receive point and change what it received, and then see if this would, assumed you had sent it over the network, trigger your vulnerability or not. It's just a question of speed. It's the same procedure as with static. Or you do what you do in static analysis as well. You follow the code. Here again, it's the good part to skip over functions if it's uninteresting. If you see they don't do anything, you can just skip over because you see they're not provided with anything relevant to your data. This is often, if you look for vulnerable functions, you know they're vulnerable, especially like string handling functions and stuff. Setting breakpoints, there would be a thing that comes to mind really quickly, because then you can see, okay, is this format string and this user data a potential overflow or not? Problem here is it's really not practical. Harvard talked about this this morning, but often you have like 1 in 100 functions being relevant to you. So what are the pros? As I said, disassembly in static is often incomplete. Just-in-time disassembly is complete. You have correct information because it's the time of execution. If the information wouldn't be correct, this software wouldn't work. And you have a known state. You actually know everything about the state this moment. It quickly uncovers format string vulnerabilities as everything else does. You again find advanced vulnerabilities pretty good. Integer overflows and wraps off by ones. It is slightly faster than static, and you need it for exception catching in fuzzing. Again, it is time consuming. Again, you need skill and experience. As I said, break and inspect is not something you want to do for library functions that are often used. It requires, apart from brain, CPU power and the binaries working and stuff, so the requirements are fairly high. You might actually run into timing issues because while you're inspecting the code, you have a connection timeout, and the application reacts differently from the normal case, where you don't have a debugger hanging on it. And unfortunately, detaching from a program is only possible when 2003 and upwards, because, I don't know, it seemed to be the right thing for Microsoft to do to kill the debuggy when you kill the debugger. So usual findings, application level overflows, again, complex vulnerabilities and integer vulnerabilities. It is, like static, really good for protocol parsers, for logging and data processing stuff, and for code using unsafe functions. For the break and inspect problematic, I thought it would be useful to have something that we have for ages in Unix, finally for Windows. This is ltrace. This is a demo implementation of what you can do with the debugger classes. It basically logs calls to any function that you specify to log. It gives you the state before and after the function call. It supports different calling conventions because I'm sick of trying to get fast call that's produced by Delphi compilers to work in IDA. You can actually select fast call, but it still doesn't really work. It is able to follow forks because now we can easily hook all the functions of the Windows API that will produce a new child. So this is what I use when I fuzz something, because if it's potentially forking with a debugger class, it's really easy to say, I need a new debugger and please put it here in this array. And then you have about 20 debuggers running because you have 20 childs. That's not a problem anymore. It supports stack analysis a little bit, so it will tell you if the target buffer is on the stack or not. And if the function has a stack frame, it will actually tell you how far it is from the return address. So all you need to find out then is how much data can you stuff into the buffer, and then you get your user root account on your not-so-user machine. And of course, it supports format string analysis because that's easy and comes for free. So this is how it looks like. I just need to uncover the slide again. Damn. Ah. Yeah. The trace definitions are native C. So you can basically, let's just go ahead and use the example here. You can basically just take your documentation files or your legitimate or illegitimate copy of MSDN and copy the function prototypes out. It supports direction for the arguments. So for example, here in ASprintf, we're not really interested how the string looks like when it entered sprintf because, yeah, that's probably just crap. But we are only interested in how it looks like when it comes out. The same in the opposite direction for the format string. We are not interested in how the format string looks like after the sprintf is done. Yeah, and other than that, it's just calling conventions, return type. It supports a few special types, as you see. FMT char just means this is a format string. So please check if there is a format specifier in there. And it supports something that I call buffer matching. So if you have a few thousand calls to sprintf, because this programmer was really, really talented, and you only want to see the ones that you influence, send the word hexer to the service and write this in a trace definition. You only see things where hexer is sprintf somewhere. So this is an example how it looks like when it logs a sprintf. In this case, we have a %s here. It tells us where the %s comes from, which is interesting because if this here does not contain a format specifier, but comes still from some R data section, it is not a format string vulnerability because it's in the binary and not provided by the user. In this case, it has a format string, and it comes from the main image data section. It tells us how many characters it wrote, what came out of it, where the buffer is, stuff like that. Fairly handy. So let's see, here's a different example. Get it back? Right. So you also often have functions that you identified in static analysis as being suspicious, and well, you don't have a name for it, because usually if you specify sprintf here, the tracer will take care about hooking every sprintf that is in every DLL or main image that's used. So for example, sprintf shows up in msvcrt.dll. If you have a newer application, you will have it in MSVCRT 7.0.dll as well, and you have a incarnation of sprintf in NTDLL. Now, this one actually hooks all three of them and makes sure that you get every sprintf call. If you don't have a name for the thing, because it is in the main image as it is here, then you just specify the address. And here I had the first parameter was something that I wasn't really concerned about, because it was always 0 when it got called. So this is just, yeah, you define it void and nobody cares about it anymore. And this is actually a logging function, and message is a fairly complex structure where it logs the message, the logging message in. And here we have a typical case where it automatically identified a format string vulnerability, and this blah over here was actually user-provided input. So the good thing about that is this, from the time having the exe file and being able to run it in the first place to the time I had a format string vulnerability and exploit ready was less than an hour. So what are the pros for call tracing? It's extremely fast, as I just said. If you don't care about the vulnerability, if you don't really care about complete coverage, all you want to have is an O-day to own someone, you take this method. You need no disassembly because you only see back-translated stuff that almost looks like C. You quickly, really quickly identify user-supplied data. For example, if you test a web server and you attach the tracer on it and look for a vulnerability in string functions, you see what's user-supplied. You can identify something that says Mozilla version 4.0. That's probably user data. If you don't recognize that, stop doing bug research. And of course, automatic format string vulnerability detection, that's cheap, that can be done in every possible way. Cons, again, it's incomplete. Only stuff that you trigger is actually logged, of course. It covers only functions. So if you have something like a copy from a string from A to B using pointer arithmetic in a loop, this will not show up. For this, you need harvest tools. And it does not yet identify compiled incarnations that are in the main image. Stuff that IDA does with the FLIR technology, library function identification. This I didn't get around to code so far. So here we have again a interesting overflow in this nice little server, which also comes with the FTP server actually. It is again a logging buffer overflow, and here we have an sprintf with a format specifier that basically just creates 2 characters out of 1, the hex representation of it. This is done in, interesting enough, in the FTP server. If the FTP server thinks that you try to buffer overflow it, and if this string that you send over is really long, the programmer wanted to be really smart and write it in hex in the log file and say, this string is really long, so I didn't handle it. But yeah, unfortunately, if the string is long enough, he overwrites a static buffer in the logging function with the string you just supplied. So I wonder how that is. Interesting here is it would be very hard to find with static analysis, because in static analysis, you would go ahead and just look at the format string and say, well, this only produces 2 characters. I can't overflow a buffer with that. Ignore the last statement if you use harvest tools. And of course, again, it gave you NT authority system remotely, so it's even rewarding. The best way to do vulnerability research is to combine forces. This is, for example, those are just 3 examples. You should actually, depending on the target you're handling, choose your weapons yourself. But a good thing would be fuzzing using Peach and a well-designed script, and attach a debugger or the tracer to it to make sure that you catch all the exceptions triggered. Call tracing, and then manually testing using the existing client. This proved to be very effective, especially in the case of encrypted protocols or compressed protocols, because there, if you don't want to implement the whole PKI stuff and the whole compression stuff in the first place before you can start testing it, you basically take the tracer, identify the function that does the decryption, and tell it to log the output of the decryption. This way, you have a different version, a different way of sniffing the data. You're sniffing the data now out of the process memory just instead out of the network. No big difference, but it would be very hard otherwise to find out what's going on inside the protocol, because there's probably not much vulnerability in the compression. And then you write a script for sending suspected overflow data once you've found the overflow. Or you go ahead and use disassembly, static analysis, and then use CMA manual fuzzing in combination with that to find out if your assumptions about overflowable or not are true. So summary, different vulnerability testing methods all have their pros and cons. The goal here was not to be extremely lead. The goal here was to show people who didn't do that before that it is not black magic. So this is how you get your own O-Day. For quick bug finding, use something automatic. Use a fuzzer, use a tracer, whatever. Just use something automatic if you need just one O-Day really quick. For real analysis,